All right, so we're going to keep going through section 4.3. We're in chapter 4, polynomials and rational functions. So rational functions, we have to define what they are and learn their properties. So specifically, we're going to define what a rational function is and determine what its domain is. Remember, domain is what are you allowed to plug in. We're going to find what are called vertical asymptotes of a rational function, which is very highly related to the question of domain. Then later at the end, which will end up in a different video, we'll find horizontal or what are called oblique or slant asymptotes of rational functions. That's the goal of this section. So a rational function is just a polynomial over a polynomial. If you take one polynomial and divide it by another, the result is probably no longer a polynomial. What it is called a rational function. It is a ratio of two different polynomials. Now, the domain of the polynomial in the numerator is everything. The domain of the polynomial in the denominator is everything. So what's the domain of the ratio? Everything except where the denominator is 0, because you're not allowed to divide by 0. So the only obstruction here is you don't want to divide by 0. So let's look at the following rational function. The numerator is 3x squared minus 5. That's a nice polynomial of degree 2. The denominator is the polynomial x plus 2. That's a linear polynomial, a polynomial of degree 1. So the domain is all real numbers except where the denominator is 0. Where is the denominator 0? If x is minus 2. So the domain is all of the x's that aren't equal to minus 2. How about the polynomial 1 over x squared minus 25? Now the numerator is the constant 1. That's a degree 0 polynomial. The denominator is x squared minus 25. That's a quadratic or a degree 2 polynomial. So the domain is everything except what makes the denominator 0. And since the denominator is a difference of two squares, x squared minus 25, it factors as x minus 5x plus 5. So the domain is everything except plus or minus 5, because that would have made the denominator 0, and that's bad. Okay, how about the domain of this one? Well, the numerator is 2x cubed. That's a cubic or degree 3 polynomial. The denominator, x squared plus 1, a quadratic or degree 2 polynomial. So to find the domain, we'd say all x except where the denominator is 0. But that says x squared is minus 1, and the square of a real number can never be negative. So there are no solutions here. In other words, there are no obstructions to the domain. So the domain is all real numbers. Now, this is an interesting example. X squared minus 4 over x minus 2. Here is your first level of analysis. The numerator, degree 2. Denominator, degree 1. They're both polynomials. This is a rational function. The only obstruction is I don't want to divide by 0, so I don't want x to be 2. Oops, sorry. But if you overthink this is, by the way, totally correct. If you overthink it, however, you might say x squared minus 4 over x minus 2. Well, let's take a look at that numerator. It's a difference of two squares, x squared minus 4. So it factors as x plus 2 times x minus 2. And now I have x minus 2 over x minus 2, and those cancel each other out. And you might think, so this is just x plus 2, whose domain is all numbers. That's kind of correct, but not correct, by which I mean it's wrong. Okay? The domain of x plus 2 is definitely all real numbers, but the domain of the function we started with isn't. And the error was in this step right here. X minus 2 over x minus 2, when you, quote, cancel something out, end quote, what you're doing is you're saying it equals 1, so I don't have to bother writing it. Is x minus 2 over x minus 2 equal to 1? That's true, except when x is 2. Because if x is 2, over here I'd have 0 over 0, which is just not even a number. It's not equal to 1. So canceling something out, always remember you're only allowed to cancel something out if you're not trying to cancel out a 0. Okay, so in this example, just to refresh, if all you did was look at the beginning and say, I don't want the denominator to be 0, so it's all x other than 2, totally correct. If you overthought it and tried to simplify it, you could easily fall into a mistake of doing a cancellation without thinking very hard and saying, oh, I canceled out x minus 2 over x minus 2, but that itself tells me x can't be 2. As long as x isn't 2, we get out exactly this. But if x is 2, the original function doesn't even exist. Okay, here's another example. Analyze the graph of the following. So what's the domain? Well, I don't want to divide by 0, so I don't want x to be 0. There is no y-intercept because how do I find the y-intercept? I let x be 0 and I just plug that in, but I can't let x be 0, so there is no y-intercept. There's also no x-intercept. If you set y equal to 0, you'd be trying to solve 1 over x squared equals 0, but 1 over something can never equal 0, so there are no solutions. Which means there's also no x-intercept. So there are no intercepts at all. Okay, so neither of the axes is ever touched by this graph. Okay, but you can observe that this denominator is an even degree polynomial, which means plugging in a positive or negative x doesn't matter. This function is even, so it is a symmetric function with respect to the y-axis. Also, x squared is always positive, which means 1 over x squared is always positive. So these outputs are always positive. So whatever the graph looks like, I have symmetry across this axis, and I'm never down here. I never have any negative values. But I don't touch this axis, and I don't touch this axis because there are no intercepts. Okay. So what you can observe, if x is very small, the output is getting really, really big. Conversely, if x is really, really big, the output is really, really small. This is a general phenomenon of 1 over something. 1 over a big number is small, but 1 over a small number is big. Okay. So as x is getting smaller and smaller, closer and closer to 0, the output is just growing and becoming huge. As x gets tiny, 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 1 over x squared gets bigger and bigger and bigger. Okay. The calculus notation, which you don't have to worry about for now, just says the limit as x goes to 0 is infinite. As x is getting closer and closer to 0, the limit is infinite. Okay, and conversely, as x gets bigger and bigger and bigger, the output is getting smaller and smaller and smaller. So, first of all, remember that the function did have this symmetry. So I'm really just going to focus on plotting the positive x values, and then I'll immediately get out the mirror image for negative x values. As x gets closer and closer to 0, the output gets higher and higher and higher. But as x gets bigger and bigger and bigger, the output gets lower and lower and lower. And then I just have the mirror image reflection here. Okay. So let's do another example. Can you graph this? Bear in mind, we did just learn how to graph 1 over x squared. So can you use some transformations to graph this function? I'll pause. I suggest you also pause and do it by hand first. So the domain is everything except -1, because that's where that denominator would be 0. What we're going to do is we're going to start with the graph we just did, but it shifts 1 to the left, and then it shifts down by 2. So this, we started with the graph of 1 over x squared. Okay. Here's what we're working towards. And the first step is shift left by 1, then do the -2 to go down by 2. And observe, the original graph, 1 over x squared, had this forbidden value of x equals 0. When we shift it 1 unit to the left, now our forbidden value is x equals -1, which is wrong. Good job, book. This should have been shifted to the right. Because the forbidden value is x equals +1. So at this stage, it should really look like this. And then I shift down by 2, and it should look something like this at the end. The forbidden value was x equals 1, not x equals minus 1. I apologize for that. Okay, so we'll end this video here. I apologize for the error in the last example. The book just made an error with a left shift instead of a right shift, but come on back and we'll keep doing examples like this.